you for coming to the presentation. My name is Mohammed Hamadi. I'm a PGR researcher in my third year under the supervision of Markel, Vigo, and Sarah Clinch. Apologies in advance about my voice. I was hoping it's going to be better than this, but it's definitely a down day, a bad voice week. In this presentation, I'll talk about a user study where we were able to model user strategies and improve user performance on interactive dashboards. An interactive dashboard is a data visualization tool that can help us view and interact with complex underlying data in the form using visualizations such as charts, maps, and tables. The adoption of dashboards has increased lately. As we saw, many dashboards being created by World Health agencies that communicate the spread and the evolution of COVID-19 virus to the public and to the media. But the problem is that users are still facing challenges with using and interacting with dashboards. If we take, for example, a project such as We Rate COVID Dashboards, that rates COVID dashboards based on their visual presentation, navigation, and data detail. Out of 369 reviewed dashboards, no more than 1% received the highest rating, which reflects the magnitude of the problem. Our goals in this experiment were to firstly improve user performance in terms of effectiveness, efficiency, and cognitive load, but we will come to this. And to detect problematic strategies, as these can be indicators of problems facing users, and if we can detect them in real time, then we can intervene to adapt the dashboards accordingly. So we had three hypotheses. The first one was that addressing user challenges using adaptations can improve user performance in terms of the three aspects that I will talk about: the effectiveness, efficiency, and cognitive load. And the second one was that the level of graph literacy users have can impact their performance on dashboards while using the dashboards. The third one was that users employ different interaction strategies on problematic as compared to adapted or problem-free dashboards. In our experimental design, we had a 4x2x5 randomized within subjects factorial design. We had three independent variables. Firstly, our first independent variable was the problems that were seeded into the dashboard. First one being information overload, where the dashboard shows too much information to the user to the extent that inhibits or impacts their decision-making negatively. The second problem was inappropriate data order and grouping, where the data and the information shown on the dashboard does not follow a coherent narrative and does not facilitate meaningful comparison. The third problem was ineffective data presentation, where some charts are more effective than others at communicating the data to the user. For example, if we compare bar charts to pie charts. The fourth problem is misalignment in visual literacy expectations, where the visual literacy expected by the developers when they create the dashboards does not align with that of the users, with the actual one of the users, and the gap creates a problem. The second independent variable was the dashboard type. So we had two types: problematic, where these problems exist, or adapted, where these do not exist. The third one was the user graph literacy, where we gauged participants' graph literacy levels using a standardized test. And their scores ranged from 0 to 4, 0 being the lowest, 4 being the highest. We measured three dependent variables: effectiveness, efficiency, and cognitive load. Effectiveness was 0 or 1, 0 for any wrong answer, or 1 for the correct answer. And then efficiency, which was the time it took each participant to complete their tasks. Cognitive load is reported by the users on 6 subscales using NASA TLX questionnaire. While users were doing the experiment, we collected interaction data, which using UseVit tool, which gave us low-level interaction data, such as event type, URLs, timestamps, node information. This is an example of one event given by the tool in JSON format. On average, each user generated 22,000 events in their session. We did some pre-processing of the data to make it more manageable, more manageable and more easier to analyze later. In terms of the results, firstly for effectiveness, we did find that users indeed improved on the adaptive dashboards as compared to the problematic ones, evidenced by the correct answers given on the adaptive dashboards compared to the other variant. We also found that two problems improved significantly, namely information overload and ineffective data presentation on the adaptive dashboard, of course. And then one problem improved on the adaptive dashboard, which was the misalignment in visual literacy expectation, but it did not improve significantly. That leaves, of course, one problem that deteriorated, did not improve. If we look from the lens of the graph literacy or at effectiveness, we found that users on the lower end of the graph literacy spectrum improved significantly on the adaptive dashboards, while users on the higher end, those who scored 3 and 4, more graph literate, did also improve, but not significantly. In terms of the efficiency, we did not find significant improvement in the completion time between the adaptive and information dashboards, though we found differences between people based on their graph literacy level, namely those who scored 2 and those who scored 3. So 2 were the ones who finished the experiment the fastest, and 3 were the ones who finished the last, or the slowest. In terms of the perceived cognitive demand and perceived performance, we found an interesting finding here, where users on the with the lowest graph literacy reported highest perceived performance and the lowest cognitive demand, while in fact, objectively, they had the lowest performance, they had the lowest effectiveness and the lowest efficiency. In terms of the navigation strategies, we firstly took the events, all of the events. We did sequential pattern mining on them to find the patterns. After that, we aimed to analyze the top 100 patterns for each dashboard. And we did thematic analysis on these patterns to reach the strategies. Emerged themes were 6. First one was visual exploration, where users hover over charts or other items on the dashboard, and then filtering to reach the required information, or customization to alter their charts to their liking. In the problematic dashboards, we found that as the number of patterns increase, effectiveness decreases. This was true for all of the investigated problems. We found extensive exploration to be associated with lower effectiveness and lower efficiency. Extensive exploration is where there's a lot of exploration in the found pattern. On the adaptive dashboard, we found that as the number of patterns decreases, efficiency increases. This was true for all of the problems, except information overload, where users had to use filters to reach the required information. We found on the adaptive dashboards that customization was associated, there was a clear association between customization and higher effectiveness. And the most common strategy here was visual exploration, which is lighter than extensive exploration compared in the problematic dashboard. On both dashboards, the most common strategy was exploration and filtering. And we also found that the exploration of the top left chart, which usually is here, top left chart, was a very common behavior, even when that chart was irrelevant to the task. Now we revisit our hypotheses. The first one held true in terms of effectiveness. So addressing user challenges using adaptations improved users' effectiveness, but not efficiency or cognitive load. Information overload was the problem that benefited the most from our adaptations, which indicates that reducing the number of stimuli in dashboards can improve users' effectiveness, but not necessarily efficiency. Our second hypothesis held true. as we found that the level of graph literacy indeed impacts user performance. Those who score 0, 1, or 2 on the lower end of the graph literacy spectrum improve significantly. Our third hypothesis also held true. We found distinctive strategies between the strategies that were employed on the problematic dashboards as opposed to the ones on the adapted or problem-free dashboards. What does this mean for user modeling? Our interaction analysis and user modeling helped us identify problematic strategies, yes, but more importantly, it helped us identify those who were struggling but were unaware, namely those on the lower end of the graph literacy. As we said, they are the ones who are in need of the adaptations, but in fact, they are perceiving themselves to have a great performance, the best performance, and the lowest cognitive demand, which raises a very important question. How can we help them? And whether our interventions can lead us to unforeseen and unexpected consequences. In either way, identifying problematic strategies can open up avenues for automatic adaptations by, as I said, if we can detect them in real time, we can adapt the dashboards, we can show tips in real time, we can highlight typical task relevant areas, or we can show different suggestions such as displaying different information to the user. With these takeaway findings, I conclude my presentation. Thank you very much.
Do you have any questions? Do you have time for questions? Yes, sir.
So how do you bring data to assess the user experience? How do you collect data?
So we did an
Repeat. It's difficult for people to hear the question. Can you repeat the question?
So he asked, how do we collect data, right?
Yes.
To analyze. So the data was collected through an experiment. It was a user study. It was done online. Users log into or go to a website. They interact with dashboards. They answer some questions, and we time their we basically time them from their start to the end to see how much they took and the answers they gave, and we analyzed them.
Yes. So it's like data analyst job.
Sorry, what's the question?
It's like data analyst.
So we need to analyze the data when we collect it. He's asking if it's a data analyst job. Yeah,
which is the part before the data scientist. But as a data scientist, the visualization of the data, and therefore you need to create models.
Oh, you mean the users? Okay. So you mean the participants look at the data, or interact with the data as if they were a data analyst.
Yes, probably that.
Yeah, I mean, look, we chose. That's a very good question actually, because we chose a type of stimuli, or the dashboards we used were COVID-19 dashboards, with the assumption that everyone would understand. As I said, many dashboards have been created in the pandemic. Many people, if you turn on BBC or CNN, you will definitely see charts, and you will hear flattening with a curve, and everyone understood to some extent there's the charts and how to read them. So COVID-19 data, we assume that people will understand them without prior background. So they're not data analysts in that sense. They are just normal people. We did not require any specific background from the participants.
I think no questions. Can you repeat that? Is that answered?
I was also about to ask whether this is a questionnaire or is it a real dashboard?
It's a real dashboard.
Okay. One thing you mentioned that intrigued me. You talked about the correlation between the increasing number of patterns used and decreasing effectiveness or decreasing